work through our mole unit review. Left off in question 8 here. Alright, so question 8 talks about Annie throwing a party, and she wants to buy enough dry ice to fill a 150,000 liter living room. And so the question says she's buying 350 kilograms of dry ice. Of course, dry ice is carbon dioxide, solid form. And the question is, will it produce enough gas to fill her living room? Okay, so we've got a couple of things given here. We have the volume of her living room, and we have the mass of the dry ice. And the question is the dry ice enough for the living room? So I guess there's a couple of ways to go about this question. We could start with a volume of the living room and then figure out how much dry ice you would need to fill it. Or you could start with this amount of dry ice and answer how much it will make, what volume it'll make when it sublimates, and then ask if it's bigger or smaller than 150,000 liters. In other words, we can start here at the volume of her room and then find out what mass of carbon dioxide would be needed, or we could start with the mass of carbon dioxide that she bought and ask, is it going to fill that room? Okay. We'll start with this one here. So we'll start here and we'll just figure out what volume 350 kilograms of carbon dioxide will make, and from there see if it's enough to fill the room. Okay, so we'll start with 350 kilograms of dry ice, which is carbon dioxide. Okay, now we tend to have units on our heart of the mole sheet, and that implies usually the sort of unit that you want if you're going to begin. And so if we want to start down here, we're going to need to start by converting our kilograms into units of grams. And that's because molar mass is typically expressed in grams. So the first thing we need to do is convert this into a number of grams. And I know that 1,000 grams is the same thing as 1 kilogram. So I can put 1 kilogram of CO2 down here, and 1,000 grams of carbon dioxide up here. Okay, I'd like to just take a second to cross those units out. And then we'll say, okay, so we've got mass in grams now, and in order to go up to the moles, we're going to need the molar mass of carbon dioxide. Now, in our last question, we found the molar mass of carbon dioxide. It was 44.0 grams per mole, so we'll just use that again down here. So we can say 44.0 grams of carbon dioxide is equivalent to 1 mole of carbon dioxide, and that cancels out our units of grams of carbon dioxide. Okay, now we have moles. And the question is, well, what volume will this make if it's turned into a gas at standard temperature and pressure? And so to do that, we're going to cancel out our units of moles and replace it with this volume here, because 1 mole of gas occupies 22.4 liters of space at standard temperature and pressure. So that's 22.4 liters carbon dioxide for every 1 mole of CO2. Okay, and lastly, our moles of carbon dioxide cancel, and we have some number of liters. So when we're all finished, it looks like we have 3 sig figs, 3 sig figs, infinity. Oh, there's only 2 significant figures here. 2 sig figs, because that 0 separates our measurement from the decimal point. So we'll just grab a calculator here and just punch this in. 350 times 1,000 times 1, which I won't bother typing in, times 22.4. And then I'll make sure to divide by that molar mass, divide by 44. And so we get a volume of, it looks like 180,000 liters of CO2. And so what that tells us, compare it back back to the question now, which asks us if it was enough to fill our 1,500 liter, or pardon me, 150,000 liter living room. And the answer is yes. So if we're asked a yes or no question, we should say yes or no. We should actually answer the question at hand. Yes, 350 kilograms of dry ice will fill Annie's living room. Okay, so let's move on then, on to question 9 here. Okay, so we've got a question, Caitlin isolates some mystery substance in the lab. Now this happens in chemistry sometimes when you're making new materials. You might make something, you have to figure out, well, what properties does it have? Maybe I can compare it to other things. So the total sample weighed 20.4 grams. So we have a weight of our sample of 20.4 grams, and it occupies a volume of 45.65 mils. And the question is, what's its density? Well, if we look on our heart of the mole sheet, we're going to find actually this is a sheet that's used for converting values, but it is not for, say, finding molarity. It's not for finding density, or for finding molar mass for that matter. So we need to know something else in order to answer this question. Now, say we can't remember what density means. That's fine. We look on the front here and we say, oh, okay, at least I've got some idea it converts between mass and volume, which means it's got a mass quantity and a volume quantity. And that might help me jog my memory a little bit, but maybe not sufficiently. So remember, we went over some TNT in preparation for this test. So one of the things we talked about is how density is just equal to the mass of a substance divided by the volume. And so we just have to take the mass of Caitlin's sample here, which is 20.4 grams, and divide it by the volume, which is 45.65 mils. 5.65 mils, and that's really it. So I'll grab a calculator. 20.4, nope, 0.4 divided by 45.65, and I get 1, 2, 3 sig figs here, so I'm going to round that to 3 significant figures, so it should become 0.447, and the units, none of them canceled out actually, so our expression has both units, grams per mil. And that's the density of Caitlin's sample. Okay. So that's pretty straightforward. That's just a kind of a reminder on what density is. And so let's move on to the next question here, which is actually going to require us to use a density quantity. Now, this is a question from a quiz we gave last spring. Okay. So let's have a look here. It says Jesse is constructing a scale, but he doesn't have any standard weights. Okay, so he decides he can look up the density of table sugar. And so we're talking about table sugar here. And then use measuring cups to figure out some standard weights. Okay. So if Jesse weighs out one measuring cup of table sugar, the question we might want to ask is, well, how many moles of sucrose will he have measured out? Okay, and also we're given some reference values here. We know that table sugar is the same thing as sucrose, and sucrose has a formula here. And by highlighting it, it's kind of harder to read now. I think I'll use that yellow. It makes it a little bit less shiny. And we're told the density, okay, and we're also told the molar mass. which is handy because it's kind of a pain to find the molar mass of some of these larger organic molecules like sucrose. Okay, so we've got a lot of information, and the question is, where are we and where are we trying to get? Well, we're told that Jesse has a measuring cup, which is 237 milliliters of table sugar. Okay, 237 milliliters, that's a volume. And so we've got volume in 3 different positions on this sheet. The question is table sugar a solution? Is it a gas at standard temperature and pressure? Or is it a solid or a pure liquid? Now, table sugar is a solid at room temperature, so actually that means we live here. So we're going to start here, and the question asks how many moles of sucrose will we have measured out. So that's really asking us to get to here. So we have to follow this path. Looks like we're going to multiply by our density and then divide by our molar mass. Okay. So just write a question 10 here, and so we're going to begin with 237 milliliters. Okay, and the first step here is it says we're going to use our density as a conversion factor to find the mass. Okay, so our density is listed here is 1.59 grams for every milliliter. And if I multiply by the density, what I mean is I can be writing 1.59 grams for every 1 milliliter. So when we say we multiply by the density, we mean multiply by the numerical value, which happens to be in the numerator here. Okay, and of course we're talking about sucrose, right? So I'll just write that in there. Okay. And that's going to give us some mass quantity. Now we need to turn to moles. So we're going to use the conversion factor here, and we're going to use the molar mass that we're given. So we don't have to calculate the molar mass in this case. So it just gives us 342 grams per mole. Okay. So as this last step, we'll I guess cancel out units of grams, so 342 grams of sucrose for every 1 mole of sucrose. And then I just take a second to check to make sure all my units cancel out. So my units of milliliters cancel out, my grams of sucrose cancel out, and I get moles of sucrose. So I'll get my calculator out and say, okay, 237 times 0.59, and it looks like I'll divide by 342, and we get a value, and looks like we have 3 sig figs, 3 sig figs, 3 sig figs. So we'll round that answer to 3 significant figures. So we say 1.10, and the units that didn't cancel out are moles of sucrose. Moles sucrose. Okay, so we're getting there, guys. Let's take a look at question 11. This is also a question from a quiz last year. I was adapted from it, at least. Alright, so Grace is making gunpowder for a mortar shell she's creating. And she knows she'll need at least 2.3 moles of potassium nitrate to make all the sulfur and charcoal react. Because gunpowder is just potassium nitrate, sulfur, and charcoal. Now she's concerned about making all the reactants fit inside her shell. And the question is, what's the minimum volume of potassium nitrate that Grace will need in order to make sure all the sulfur and the charcoal react? So it looks like we're given an amount of moles, and we're asked to find the volume of this salt, potassium nitrate. So potassium nitrate is defined down here as KNO3. We're given its density, and we're told its molar mass. Okay. So it looks like here we know we're going to need 2.3 moles of potassium nitrate. So we're going to begin here. And the question asks us to find a volume. So the last thing we'll need to know is that potassium nitrate is not a gas, or it doesn't say anything about it being a solution. So it's actually just going to be a salt, a pure solid. So we're going to go down here from the moles, using the molar mass, which is given, and then convert that into a volume. Okay. Maybe we'll just start on the page here. Wait, where is all my paper? Oh, it's right here. Okay. That is senior moment. Okay. So, question 11. So, the first thing we know is that we're beginning with 2.3 moles of KNO3, potassium nitrate. Okay. And I want to change my number of moles into a mass. And I'm going to use the molar mass to do that. And the molar mass is given. The molar mass is 101.1 grams for every 1 mole. So 101.1 grams of KNO3 for every 1 mole of KNO3. Okay, so that tells me the mass. But that's not quite what we were looking for. We were concerned about the volume fitting into a shell here. So the last thing we need to do is find out the volume. And so this arrow here suggests we're going to divide by the density. So let me just clarify what I mean by that. Every density unit has slightly different, value has slightly different units. Grams per cubic centimeter, grams per milliliter, kilograms per liter. And so when we say we're dividing by density, what we mean is that in this case the gram term is going to go on the bottom, 2.11 grams of potassium nitrate. And on the top is going to be the volume quantity, so 1 centimeter cubed. Okay. And so as this conversion factor is set up, we'll be dividing by the value 2.11. And lastly, our grams of potassium nitrate cancel out. Okay. So just grab a calculator and punch this stuff in. So I've got 2.3 multiplied by 101.1, and I'll divide it by 2.11. And I get a value. I should be rounding it to 2 significant figures. So 110 to imply that this, so it looks like 110 shows me 2 significant figures here, and the units here are cubic centimeters of potassium nitrate. Now, a cubic centimeter is a measure of volume, right? You can picture a 1 by 1 by 1 cube, right? And that's what a cubic centimeter is. 1 centimeter, and to be 1 centimeter deep. And if you had 110 of those little blocks, that would be the volume of the potassium nitrate Grace is needing. Of course, that's the same thing as a milliliter as well. So you could also think of it being 110 milliliters of potassium nitrate. You're not required to do that. Cubic centimeters are a legitimate unit of volume, so that's fine. Okay. Let's move on. So question 12 here asks, what's the molarity of a solution? Okay, so we're looking for the molarity. And we know that we're dissolving 20.0 grams of H3PO4, which is phosphoric acid. And we have a volume of 50.0 mils of water. Okay, so just like the density question in question 9, we don't have a conversion factor, or we don't have a way with this sheet to answer a question about what the molarity is, just like we didn't have one that answered what the density is. Molarity is a concentration and expresses the number of moles for every 1 liter. So to answer this question, we have to know our T&T terms that we were practicing. We have to just know that molarity equals the number of moles of solute divided by the volume of your solution. Okay. So what are we given here? We know the volume of our solution, but we don't know the number of moles. We have the mass of our solution, or of our solute. Now, if we have the mass of our solute, we can find the number of moles, but we're going to have to find the molar mass of H3PO4. So we're going to start by finding the molar mass of H3PO4. And to do that, we've got 3 hydrogens. So we'll have 3 times 1.0 grams per mole, which is 3.0 grams per mole. And then I'll have my phosphorus here, which I can see on my periodic table, has a molar mass of 1. Sorry, pardon me. There is 1 of them, and it'll be 31.0 grams per mole. So that just gives me 31.0 grams per mole. And then lastly, I've got 4 oxygens. So it's 4 times 16.0 grams per mole. You don't have to write all of these steps out, but I do need to see some work. I'm just writing all these steps out so you can follow it in case finding molar masses is confusing. Okay, and then we just add all these together. So I get 0.0 grams per mole, 3 plus 1. I get 8, and looks like 98.0 grams per mole is my molar mass of phosphoric acid. Okay, so if I have 20.0 grams of H3PO4, I can convert that into a number of moles by canceling out my grams down here on the bottom diagonally and replacing it with 1 mole H3PO4 up here. And these grams cancel out, and I can just do a division here. So it's 20 divided by 98. And I should get 3 significant figures, or 3 sig figs here and 3 sig figs here. Remember, if we add an extra decimal, we move our zeros off into the decimals. Those imply that we know our values to the tenths of grams in this case. So we should express this as 0.204 moles H3PO4. Now, the last thing we need to do is find the volume. Now, molarity is expressed in units of moles per liter. So we need to make sure we've converted our volume at 50 mils into a unit of liters. So the last thing we'll do is we'll convert 50.0 milliliters into a number of liters. And I know that there are 1,000 milliliters in 1 liter. Our milliliters cancel out, and so I just say 50 divided by 1,000 gives me 0.0500 liters of water. And now with this information, by the way, there's the calculator didn't say this 5.500, but we have 3 sig figs here. These ones just separate our 5 from the decimal place. This one is kind of irrelevant, isn't even necessary. So to imply there are 3 sig figs, we have to actually add these extra 2 zeros. Okay, now lastly, find the molarity. And so to do that, we're just going to take our number of moles of solute, 204 thousandths of a mole, H3PO4, and we divide it by our volume, 0.0500 liters. And when we punch that into a calculator, I get 0.204. I think those extra 2 decimals were 0.8. No, who cares? I don't want to complicate things. Divide by 0.05, and I get a concentration of 4.08 moles per liter of H3PO4, or I can use a capital M to express the same idea. All right. So let's take a look now at a question that requires us to use molarity, which is this last question before the challenge problems. So it gives us a concentration of seawater. Sodium concentration is 0.469 molar. Oh, I guess that's it actually. You know what? We'll call this from 1 to 12. Sorry guys, actually I have to go.